Hello, Engineering Statics, ENGR, ampersand 214, being given at Bellingham Technical College. This lecture is on forces and lines of action and serves as a review of vector addition. Vector addition is something that hopefully most of you all have seen in the mechanical part of your physics courses or in some kind of vector algebra studies you may have had in mathematics. So we're going to start with a graphical way of adding vectors, which is useful if your vectors literally represent length. So the length of the vector would represent a displacement length from one point to the other. But we're going to zero in on the algebraic way of treating vectors, because in most cases in statics your vectors are not going to represent an actual length displacement. They're going to represent a magnitude, so like a magnitude of force or moment quite often. But just say we were going to go from this point where vectors A, B, and C all intersect, and say these vectors really did represent actual physical positional displacement. So you could go from this point where my cursor is kind of hovering, you could go a certain distance in a direction of the A vector, a distance corresponding to its length, and get to this point. You could do the same with B, kind of go left to right in a straight line, maybe on a compass direction, say due east, in which that would correspond to a certain length, and you could do the same with C. So one way of graphically representing vector addition vector A plus vector B would be to follow what's called the parallelogram addition rule, where we would take vector A and we would literally displace it over such that its tail intersected with the tip of vector B, and its head would now be, oddly enough, intersecting with the head of vector C. And so we could go from our origin point a distance corresponding to the magnitude of vector B in the direction of vector B, and then do the same with vector A, and we will have ended up at the same point that we would have if we had gone straight from the origin and out vector C. So that's a way of graphically using the parallelogram addition, showing that vector B plus vector A, and I'm tracing vector A with my little cursor here as if it had been displaced there, equaling vector C. And in that graphical sense, the equality comes from the fact that we end up at the same position. Okay, that's great if you are looking at distances, and if your vector magnitudes correspond to something of interest, you can always scale your vectors graphically to the magnitude of whatever you care about and do a little graphical addition. But most of the time you're going to do the addition trigonometrically by using more of an algebraic expression, because it's not usually practical to do this parallelogram when your vectors correspond to forces or moments or anything other than actual distance. But it's something to think about in terms of how you add vectors, because you're graphically, whether you realized or not, we're including a lot of trig as you move things over and did the addition. So let's just look at the properties that vectors have kind of as numerical quantities. What rules of mathematics apply, because that tells us what order of operations we can use to manipulate them when we're trying to, like, say, figure out the sum of the forces on some object, because that's what we're really going to use them for. So say we're looking at vector A plus vector B equaling vector C, which we just showed graphically. Well, it turns out the commutative property of addition applies. So we can either add vector A to vector B and get vector C, or if we happen to have vector C, we could resolve it into vectors A and B and add their sum and have an equivalent statement. This is super important because sometimes we really care about the component of one vector that happens to be pointing in the direction of another. And so breaking a vector up into its two component parts that point in the directions we really care about is something important. So the commutative property of vector addition says, yeah, you can do that. So that's good. We can also apply the associative property, so we can group different ways. So if we add vectors A and B and get a sum and then add C, maybe presumably to get a vector D, that would be the same as if we added B to C first, going to for the what's inside the parentheses first, get that sum and then add to A. And again, there's going to be a lot of times when it's way easier to add things in different orders, and the associative property of vector addition says, yeah, you can do that. Identity property. If you have a vector and you add its opposite, its algebraic opposite, so negative A, you get 0. So graphically that would be like saying you start here at the origin and you go out, if these vectors represented displacement in length, you'd go out to this point, and then when you add vector minus A, what that just means is you come back the same amount along the same line but in the opposite direction. So that's what this graphically means. You go out here and then you turn around and come back. Again, this also could be interpreted as if you had a force or a moment A in a given direction and you applied an equal and opposite force, they would cancel out. Really important if you're trying to keep something in static equilibrium. Okay, subtracting two vectors is the same as adding the algebraic opposite, adding the inverse, the negative of it. And a scalar can be distributed over multiple vectors being added. So this is the distributive property for scalar multiplication of vectors. So alpha here doesn't have a little arrow on top, so it's just a scalar, it's just a number with units, it doesn't have a direction. You can use the distributive property of multiplication over addition to say we can multiply that scalar by each vector separately and then add the two, or we could factor it out. Okay, so let's look at a case where we might actually use that. So if you've got this box here sitting on the ground and this little crosshatch base underneath things, that represents a surface. So you'll see that in a lot of engineering schematics. That means a physical surface or the ground surface. So you have F1 pointing kind of straight out to the right, and then you have F2 pointing in a direction that's defined by this 3 across and 4 up triangle. So that 3 across and 4 up gives us an angle at the base. And so we could use some trigonometry to figure out which component of F2 is in the direction of F1 and then which is at 90 degrees to it. So I don't have the resultant force at point A, so what somebody wants to do is a question mark. So somebody says, what if I wanted to just apply a single force at A that would have the same effect as F1 and F2? So our strategy there would have to be, well, let's figure out how much total force we have in one orthogonal direction. We're just gonna define one direction as being like straight horizontal, and F1 is pulling pretty much horizontal. So we're going to define that as one direction. And then the next orthogonal direction, so F1 is kind of in the x direction, the y direction would be pointing straight up. So if we got a vector that basically had a component that was the same as F1 plus F2 in the x and the same as F1 and F2 in the y, we would have its equivalent. So what we want is an F3 that is F1 plus F2. So all we have to do is add vectors F1 and F2 and we will get the resultant force. So these are both forces. And a note about vector notation while we're going, you see I've got F1. In case you haven't figured it out, or this is something new, figured it out from context, and I apologize for not mentioning it for those who are not used to vector notation. There are two ways vectors are typically noted. If you're looking at a print textbook, quite often the difference between a scalar and a vector will be a bold font. But if you're just handwriting it, one of the ways it's common to denote a variable as being a vector is to put a little arrow over the top. So if you want to talk about the magnitude or length of a vector, you write the vector with its arrow and then put it in little vertical bars like absolute value bars. Or you take away the arrow. So both ways say the magnitude of that vector is. And of course, a magnitude is always a scalar. So somebody has told us how hard we're pulling in each of these directions. So F1 we'll take to be straight horizontal. So we're pulling with 90 pounds of force horizontally, and that's vector F1. And then we've got 100 pounds being pulled in the direction of F2. So now we know the magnitude. So now what we have to do is just add the two vectors. We're going to add F1 and F2 using direction and magnitude. So we could kind of do our little parallelogram addition here, figure out what portion of F2 is in the same direction as F1, and then have the vertical portion be on its own. And the easiest way to do that is with trig. So we've got, I threw some coordinate axes down to make my life easier. This is a unit vector I hat, which basically says I've got an x direction coordinate axis here parallel to F1. And the j hat is a unit vector that says I'm the y-axis. And here's my F2, and this angle theta is given by the inverse tangent of 4/3. Rise over run is the definition of tangent, opposite over adjacent. Out of the SOHCAHTOA, sine, cosine, tangent. So I know that the hypotenuse of that 3, 4 is 5. It's a 3, 4, 5 right triangle. So if I wanted to just get the vertical component of F2, I would take its full amount, its full magnitude of 100 pounds, and I'd multiply by sine theta, which is of course the portion that's only vertical. And if I wanted the horizontal part, I would multiply by my 100 pounds by cosine theta, which is 3/5, adjacent over hypotenuse, opposite over hypotenuse for sine. And so that resolves vector F2 into an I hat and j hat directions. F1, of course, is all in the I hat or x direction. So it's 90 pounds all in the x direction. And so F2 is going to be split by these ratios in the x and y. So here we can write this out. I've got F2 written out in terms of its magnitude times the portion of that that's in the x direction or I hat direction. I'm using unit vector notation to denote x and y coordinate axes to get you into practice, because that's the most common way the x, y, z Cartesian coordinates are represented in vector notation. It's with unit vectors, which we will go over explicitly later, but we're getting some practice now. Okay, so now we need the vertical part. So the y-axis, which is j hat times sine theta, which we already figured out from our 3, 4, 5 right triangle. So now remember, we can multiply a scalar and distribute it over two vectors. Well, because I used a unit vector to represent my x and y, each of these two components in parentheses is a little vector. It's a little vector. A unit vector has a length of 1, by the way. So it just tells you direction. It's pure direction. So I have cosine theta in the x direction, no length. All of its length is coming from the cosine theta. And I have sine theta in the y direction. So I'm going to distribute that 100 pounds over the x and y components, and I'll evaluate cosine theta using my little fraction and multiply out, and I actually get whole numbers, which is convenient. So I end up with 60 pounds in the x direction, which is horizontal, and I get 80 pounds in the vertical direction. Now I had F1 as well, which was 90 pounds, and it was all in the horizontal or I hat, meaning unit vector in the I direction. So if I add two vectors, I'm going to add by direction. So I add x's to x's, y's to y's, z's to z's. So I hats get added to I hats, j hats get added to j hats, and if I had a z-axis 3D, it would be the k hat unit vector. So my combined, my vector sum, I'll just call it F3, is going to be 60 pounds in the x plus 90 pounds in the x plus 80 pounds in the y. So I have 150 pounds pulling in the x direction horizontal, and I have 80 pounds pulling in the vertical direction. So this is actually my answer. This is a way of writing my my vector sum. If I wanted to attach a rope and pull with a force that's equal to F1 and F2, I got to have one rope that's oriented in this direction, and if I wanted to get its magnitude, of course I could just use the Pythagorean theorem and do 80 pounds squared plus 150 pounds squared and take the square root. So I could get a magnitude from it. So there's my vector sum. I just added two vectors and got a force resultant. Very important for statics. Okay, so I'll go over one more example here, and then I will give you the highlights. This is a long example that I would highly recommend you go through. Okay, we got a little eyelet that's sticking out of a wall, and we have one vector pulling straight up, and we have another pulling it at 30 degrees of vertical, and then we have another one pulling downwards at 45 degrees below the horizontal. So this angle 45 degrees is with respect to the horizontal. So somebody wants to know what magnitudes of F1 and F2 would give an F3 magnitude of 10 pounds in the direction shown. So somebody said basically, if we've got F3 and its magnitude is 10 pounds, what magnitude would F1 and F2 have? Now we have directions for everything, and somebody gave us a magnitude for one vector, so all we need to know are the scalar portions of the other two. So this is, believe it or not, this is just a vector addition problem. So what we're going to do is we're going to resolve F1, 2, and 3 into their XY coordinate components. So we're going to resolve all of those vectors into vertical and horizontal components. So I deployed my friend the coordinate axes. So I slapped a coordinate system on this. So this time I have my x-axis pointing to the left and my y-axis pointing vertically upwards. It's generally not standard to do that, but I just did it for this problem. So if you're pointing to the left horizontally, you are in the I hat unit vector direction, and if you're pointing straight up, you're in the j hat unit vector direction. My third coordinate axis, if this were 3D, would be pointing back into the paper. So using the right hand rule, which we'll go over with the cross product. Okay, so my first job is to break up every vector for which I have a magnitude. So somebody give me a magnitude of 10 pounds for F3. So I've got a direction, and I've got a magnitude. So what I've got is basically F3 in polar coordinates, so to speak. So I'm going to put it in rectangular. So I'm going to write it as a sum of its component in the horizontal and vertical directions according to my unit vectors. So if I want the horizontal component, my 30 degrees we'd look at the sine of 30 degrees, and then the vertical component is the cosine of 30, given the way the angle is defined with the vertical. So I can say that F3 is equal to its magnitude times the portion of it in the horizontal, and that's sine of 30, plus its magnitude times the portion of it that's pointing in the vertical. Pretty easy. So there's our vector magnitude. I can do the same thing with all the other vectors. So I'm just going to go ahead and write all of them in terms of which fraction of them is pointing in the horizontal and which fraction is pointing in the vertical. So F2, I've got 45 degrees, so I can, with respect to the horizontal, so I can do cosine of 45, that's the part in the horizontal direction, and sine 45 is the part in the vertical, and I've noted it's got a magnitude, so it's being distributed over both portions, and F1 only has a y component. It only has a j hat component. It's pointing straight up, so it has 0% of itself in the horizontal, so it's all vertical. And we know that the magnitude of F3 is 10 pounds. So one thing you're going to find in statics problems is you will end up trying to get the same number of equations as unknowns, and you'll use your equations of equilibrium and definitions of moment and anything else you know about the problem to write a relationship, and then you'll list out all your variables, the things you don't know, And you want to have a situation where everything that you know and everything you don't know is equal, because then you get one exact solution. So you want the same number of equations as unknowns. So I just set up some relationships that I know. I just used geometry to write portions of my vectors that I know are pointing in given directions. And what I want is the magnitude of F2 and the magnitude of F1. That's what somebody asked me for. So I want to see right now, do I have enough equations to solve for both of those? So I know I'm going to have one equation that says everything in the x direction has to, to add up, and everything in the y direction has to add up. So I know F3, I know sine and cosines of angles. I don't know F2 and I don't know F1. But I'm going to end up saying something about, we want to know the magnitudes that would give an F3 in the direction shown. So basically I have, this kind of should be over there, but I'm going to have an equation that relates these two, everything in the x, and I'm going to have an equation that relates everything in the y. I'm kind of circling with my mouse around the y part. So I have two equations. I have two unknowns. Yay! I can solve this. This is something I can solve for. So the next thing I'm going to do is say, well, this isn't accelerating. I can equate all these forces, so that's really important. That's what actually gives me my relationships. So I can say the portions of each of the vectors that are in the x and in the y have to equal. So the portion of my F1 that's in the x plus my portion of F2 that's in the x is going to equal whatever portion of F3 is in the x. So there was nothing of F1 in the x. The portion of F2 that was in the x direction is my magnitude of F2 times cosine of 45, and then the portion of F3 in the x was the magnitude of F3, which is 10 pounds, times sine of 30. So hey, great, I can solve for the magnitude of F2. Just do some algebra and it's about 7.07 pounds. So that was one of the things I needed. Now all I need is the magnitude of F1. So I can plug back into a vertical equations of equilibrium. Basically we're kind of skipping ahead, but we're using this relationship and just applying it to both the horizontal and vertical parts. So I do something similar. I say, what part of the part of F1 that's in the vertical, which is all of F1, minus the part of F2 that's in the vertical, which is its magnitude times sine of 45, equals the part of F3 that's in the vertical, and remember that was its magnitude times cosine. I know its magnitude because I was given it, and I know the magnitude of F2 because I just solved for it, so now I can solve for F1. So that's my answer. Someone said, what magnitude of F1 and F2 would balance an F3 that was equal to 10 pounds? Well, you'd need to yank with 14 pounds in the F1 direction and about 7.1 pounds in the F2 direction to make that true. So that's kind of a design-based way of using vector addition to balance forces. So all we did was break forces up into their component directions, apply a little trigonometry, good old SOHCAHTOA, and that's sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. If you don't remember that from your trig studies, please review it. You will use it every day. There are a couple of other methods to do this that I'm not going to explicitly go over in this lecture. It's getting to be a bit long, but there are some rules about triangles and the relationship between the lengths of sides and the angles and the sines of the angles that are opposite to them. It's called the law of sines. It is basically a shortcut to trigonometric relationships that would be present if you dropped perpendiculars from triangles and turned them into two right triangles. You can actually derive this if you want to do a lot of trig, but it gives you a bit of a shortcut to solving problems. So you could use the law of sines to solve the same problem without necessarily going through unit vectors in a coordinate system. They're both equally valid. I personally like to put a coordinate system on things because it gives me an absolute reference to come back to and just kind of keeps track of directions very, very well, especially if I eventually want to use matrix algebra and maybe a computer program to solve something easier that's complicated. But law of sines is powerful in fields like surveying, so there's nothing wrong with doing the problem either way. You won't necessarily be asked to do things one way or another in this class, but just be aware this is a powerful relationship, and you might need it or something like it if you're struggling with geometry and you need an extra equation. But basically the law of sine says the ratio of the length of a triangle side to the sine of the angle opposite it is the same for every length and angle. So that gave us a relationship to relate portions of these vectors that were in common directions. So that was another way of doing the problem. And last but not least, we're going to bring up a topic that you may or may not have had. This is probably the most important topic with vector algebra that we'll deal with in this class. So I'm sorry that it's coming at the end of a lecture, but hang in there with me. This is unit vectors, and I just used them in my example, so I kind of gave you a glimpse into how powerful they are. A unit vector has a very specific definition. It's a vector that has the length of 1, and that's no units. It is not 1 anything, it's just 1. It's dimensionless. It has no length, no magnitude, no units. It's 1 by definition. So all it gives you is direction. It can be pointing in any direction, but its length has to be 1. The biggest use we put it to is to define the coordinate axes. So you can see here we've got our nice coordinate axes that we can apply the right-hand rule to. So we have x coming out of the paper in this direction, and then y pointing off to the right, and then z straight up. So we can define the coordinate axes with a vector if we want. And the typical notation for a unit vector in the x direction, which defines kind of the x-axis, is I with a little hat over it. So I'll refer to that as I hat. J hat defines the y direction, and K hat defines the z direction. So if we want to basically apply a force that puts 10 pounds each in the x, y, and z direction, all we'd have to do is create a vector that says 10 pounds I hat plus 10 pounds j hat plus 10 pounds k hat. And it would have a total magnitude in pounds of the square root of 300 pounds because you would use Pythagorean to get that. And so that's the other important thing to remember about vector magnitude. If you got a vector that's not a unit vector, so look, we got vector f. It's got a certain amount of it's probably a force vector. It's f. So it's got a certain portion of itself in the x direction, so we'll call it f sub x. It's pointing off in the I hat direction. And it's got a certain portion of itself pointing in the j hat direction. So I use f sub y to remind myself that the j hat direction is like the y-axis, and the same with z. Say I wanted to turn all of this into a unit vector and say, gosh, I want a unit vector that points in the direction of f but has no force. I just want the direction. Forget about the magnitude. Get rid of it. Well, all I have to do is divide the force vector or whatever vector by its own magnitude. I just divide the magnitude out. And the important thing to remember is you divide out every component with the entire magnitude. So how would I find the magnitude with 3 different components using Pythagorean? Well, as it turns out, I can apply Pythagorean in as many dimensions as I want, and I can prove that it's the 2D Pythagorean you're probably used to, which is just, like x squared plus y squared square root. We just add the square of our last component, and we can actually prove it by adding a 3D right triangle here. So basically f squared plus y squared square root is the base of this triangle that I can use to form the whole vector. So you can actually go through a little proof and prove that this is indeed the length of our vector, our 3D vector. So hey, great, we have the length. So if I wanted to create a unit vector, which I would denote as f with a little hat, I would just divide this component by all of this component by all of this, and this component by all of this, and retain our x hat, I hat, j hat, k hat directions, and then I would have an f hat. So I can, here's how I get the length of a vector, and if I want a unit vector in a direction, I just take the whole vector and divide each part by its magnitude. I don't have that written out on this slide. You will see it in other ones though. And it is a crucial skill to be able to take a vector, find its magnitude, divide out its magnitude, turn it into a pure unit vector in the direction of the original vector, and then maybe multiply by a scalar, do something else with it. Or you might want to use it just to denote direction and do something else with it. But it's a real critical skill to have. And it's a good thing it's super easy. Just remember, divide the whole length, turn that into the denominator for each of the components. And if you want to check yourself, remember, a unit vector has a magnitude of 1. So when we divide each of these I hat, j hat, k hat components by the whole 3-part Pythagorean length, each of these multipliers is going to be way less than 1. But if we squared them and added them all together and took a square root, we'll get 1. So that's it. Quick unit vectors review. Fingers crossed, maybe you've seen this in a physics or a math class before. But if not, you know the definition now, and you've got a really powerful tool that you will be using later in this course.